So today we have Artemis Spyrou from Michigan State University that will talk about nuclear astrophysics and exotics. That is very cool because it's also my topic. I'm a theorist, she's an experimentalist. So Artemis, when you're ready, we can start. Is it on? No, I don't think so. Okay, now it's fine. Hello? Yes. Yeah. If it's turned it on, if it turns off because it's low battery, just use this one and I change the battery.
Sounds good. Okay, good morning, everyone. It's my first time here. I got a little lost this morning, but I made it. And then the computer wouldn't let me come in. But anyway, I'm here. I hope you had a nice first week of the school. And I think my 5 lectures are on a pretty different topic than all the other topics you're discussing in this school. It's kind of the more, let's say, old-fashioned kind of nuclear physics, but where we keep our nuclei whole and we try to see what we can do with them. I hope by the end of at least already today, you'll see that it's not old-fashioned at all. There's so many new things happening. So I also, understanding that this is quite different from what you've been talking about, I will be trying to cover a little bit, remind you of some of the basics before jumping into what is new. So if you're already too familiar with the basics, just be patient. I'll just kind of be going back and forth. So that's my plan. Let's see. I have 5 lectures. It's 2 today, 2 tomorrow, and 1 on Wednesday. And the way I try to group them, I'll start with some exotic phenomena in rare isotopes, and this is again where we'll be going through the basics as well. And then later today, I'll do a general introduction to nuclear astrophysics, again from the various nucleosynthesis processes, with more of a focus of what are the different processes and what kind of nuclear physics do we need to understand them. And then for the last 3 lectures, I'll just go through all that different nuclear physics. How do we measure things? I am an experimentalist, so I'll talk a little bit. How do we measure things? What is important? What do we do if we cannot measure anything? How do we indirectly constrain things and so on? So that's the plan for the week. I don't have to go through every single slide I have here. I have something like 180 slides, and I'm not going to try and go through all of them. I am a lot more interested to kind of go at a certain pace, and then if you have questions, just stop there and discuss whatever you're interested in, and we cover less, but cover it in a way that is meaningful for you. Also, I've tried this setup that I'm going to propose here before with my classes and with other summer schools, and my students said that they like this more, and I'll explain what this is. So let's give it a try for today, and if you like it, we continue. If not, then we stop it. But my plan is this 40, 10, 10. We have, let's say the one lecture is 1 hour. I'm not going to talk for 1 hour. No one can listen and absorb anything for a whole hour. I'll try to keep it shorter, try to cover as much as I can. Let's say up to 40 minutes, not more. And then instead of going straight into questions, of course, if you have questions, just stop me and ask questions. But instead of going straight into a Q&A, we found that if we stop for 10 minutes and you talk with your neighbors and kind of process the material a little bit and have the time to form a question, then that works a lot better. And so then we'll do that little break where you discuss with your neighbors, and then we'll come back for the last 10 minutes for actual Q&A. Where I'll try to encourage, typically for my summer schools, I force everyone to ask a question. I'm not going to force you, but I'll kind of try to go through the whole room and see if there are questions. So that's my plan. Before starting with the physics, I wanted to do a quick introduction of who I am, just so you know who you have in front of you, and hopefully throughout the rest of the time I'm here, I'll get to meet you and learn who you guys are. I'm sure you did your introductions last week. Okay, so I am originally from Cyprus. That's where the accent is from. Everyone has an accent in physics, so mine is from Cyprus. If you're not familiar with Cyprus, it's a tiny little island country in the west part of the Mediterranean. the east part of the Mediterranean. Most people think that it's part of Greece. It's not. It's actually its own country. But it is a small country, and at the time when I was graduating high school, we didn't even have a university. There's 2 of them now, but at the time there wasn't. So most people from Cyprus would go to Greece for their studies, and that's what I did. I went to the northern part of Greece for my physics degree, and then I moved to Athens, Greece, where there's a small accelerator lab, and that's where I did my PhD. And then 2007 is when I moved to the US. I went straight to Michigan State, supposedly for a 2-year postdoc, but that's been now 15 years and I'm still there. I was at the right place at the right time, right when my postdoc was finishing. The new facility for rare isotope beams was announced, and I'll tell you all about it. And so immediately they opened faculty positions, and I got one of those. So I've been going since then through the ranks, assistant, associate professor, I'm now full professor. I had an appointment for a while as the associate director for education and outreach. I moved on from that to just being the faculty outreach advisor. So that's kind of my career. A little bit about the lab before we start, because it will be coming back, especially as we're trying to go into the more exotic phenomena and what are we trying, where is the field going? I want to introduce the lab to start with, and we'll go into details of how it works and how it produces those rare isotopes as we move along. So FRIB, we're the facility for rare isotope beams, is right in the middle of campus of Michigan State University, which is great. I think I have the next picture. So this is the lab, and the physics department is right here. It's kind of barely out of this picture. The chemistry department is this one. Engineering is just 5-minute walk. So we have students, faculty who are associated with these departments, and it's just easy to go from your research lab to your classroom and back and all the time. So this has a big advantage. We have a huge number of students at any given time, both undergraduate students and graduate students working in the lab. So we have, what I'm showing here is just the nuclear group, nuclear experiment, nuclear theory, and accelerator science. So these are the subfields included in the nuclear group. So we have 45 nuclear faculty. Anytime we have about 40 postdocs. I think now we're over 100 graduate students and about 100 undergrads. So it's a very large group. It is the #1 nuclear physics program in the US. It's a large group. It's, as I said, quite different physics than what is done here, but it's kind of the sister lab up in the north. And we have about 1,300 users from all over the world running experiments there. Just introducing the lab. I will say, since we have a lot of students, well, all students here, I will say that we have postdoc openings all the time. Being such a large group, we have at least 2 or 3 postdoc openings at any given time. Someone is looking. So if you're interested in what I'll be talking about and you want to give it a try or just find out more, let me know. You can send me an email or you can go to our website. Okay, so the lab itself, here's the lab. And again, I'll go through a lot more, but it consists of a linear accelerator. Here's the accelerator part. It accelerates anything from, not quite hydrogen, we don't typically do hydrogen, we start typically at oxygen, but anything from oxygen to uranium to about 200 MeV per nucleon. So it's relatively low energies compared to what exists here, but these are perfect energies for what we want to do, which is to produce and study these rare isotopes. Once you have, with the accelerator, we accelerate anything that is stable. So you have to start with a stable species. And then once you accelerate it, then it goes into this area where we have a target. It hits the target and breaks into pieces. That's called a fragmentation reaction. So imagine now you have a uranium, you hit a target, it really breaks into anything lighter than uranium. You're making a lot of different things. Then you go through this section here, which is a separator out of all the hundreds of nuclei that you're making to select the one or the small group that you're interested in. And again, I'll show some more examples later. And then from this point on, all of this region is different experimental stations. Depending on what you want to do with these nuclei, what it is that you want to study, you just guide them in different regions. Sometimes we want to do experiments with these for us, high energy beams, the fast beams. Sometimes we want to stop them completely and put them in a trap and measure their mass, or shine a laser on them and do laser spectroscopy, or just watch them decay and see what the decay products are. So depending on what you want to do, you can choose your energy. And the last 10 years or so, we even built a re-accelerator. That's this part over here. And that is directly related to what I'll be talking about the next couple of days, directly related to nuclear astrophysics. In an astrophysical environment, even the highest temperature, even a supernova explosion, the highest temperature you can get, if you translate that into energy, it's actually not a lot of energy. It's about 3 MeV per nucleon, give or take. And so the 200 that we're starting with is just way too high if we want to really study the reactions at the right conditions, at the right temperatures. So we have to slow them down and then re-accelerate them at the right energy. So this is this last part over here. And again, different detectors and so on to do the different experiments. So this is the lab. What I'll be talking about is not just EFRIT, it's the whole community studying this kind of nuclei. So I'll mention there's an equivalent lab at Riken in Japan, which had been up until up until now, it had been the #1 lab in terms of production of rare isotopes. EFRIT is now the next generation, so it will produce more once it's at its full power. In terms of status, EFRIT has been in the process of being built for the last 14 years or so, and we just ran the first experiment literally 2 weeks ago. So this is really fresh stuff, fresh out of the oven. Okay, so this is kind of what the lab is about and what just to set the stage. And the quality of this picture is not great, but everything we do, we put on the nuclear chart. And again, just making sure that we're all on the same page. Nuclear chart here with number of protons on this axis, number of neutrons on this axis. All the stable isotopes are shown here in black. And so these are the ones, anything that is stable in principle, we could accelerate in an accelerator. But these are not the ones that we are mostly interested in. We are interested in the ones that are unstable, the ones that are already in some color here, and even more, the ones that have not been discovered yet. They're all the way out here. So this is what we're trying to get to. But to get there, we need to understand this picture because everything we do, we try to put on this picture. The nuclear structure and nuclear astrophysics, the processes, everything we do goes here. So a few characteristics to kind of get started. Stable isotopes, as I said, are the black boxes here. And you can see that in the beginning down here, this line corresponds to a number of neutrons equal to the number of protons. So for the lightest nuclei, we have stable isotopes which are equal number of neutrons and protons. As you go a little bit heavier past calcium or something like that, then this whole chart tends to bend. Yeah.
There's like a white dot, like kind of like in the middle. What is that?
That's a very good question. I don't think it's anything. Whoever made this chart, probably. Yeah, but that's a good point. The color code of this chart, you'll see color code based on half-life, based on the masses, based on many different things. This particular version, the color code is how do these nuclei decay. So the orange ones, it's a beta plus decay. All the blue ones are beta minus decay. So beta minus, a neutron is converted into a proton. The beta plus, a proton is converted into a neutron. The heavier isotopes up here, you can have some alpha decay, a few kind of spontaneous fission. And then as you go to the extremes, out here, you get into a region where isotopes can neutron decay, and on the other side, they can proton decay. Yeah, I have no idea what that is. I should fix it for the next presentation. Okay, so there's about 250 stable isotopes. The approximate there is, there's a point, how do you call an isotope stable? In principle, you call it stable if it doesn't decay. But what if the half-life is of the order of the age of the universe? Is that stable or is it not? So that's why it's approximately 250, depending on the criterion you choose to use. There are some isotopes that we can't find naturally on Earth, like uranium, although it doesn't have really stable isotopes. So that's where this approximately is coming from. There's about 3,000 known isotopes. These are everything with the color here, about 3,000 known. And theorists predict that there's about 7,000 isotopes that exist in nature. So we still have a good way to go in terms of discovering all the available isotopes. The other thing I wanted to highlight here, I never finished why this bends over to the side. This is because, of course, protons have charge. And if you have a nucleus with only protons, the protons would repel each other. And so then you would not end up with a bound system. Adding neutrons helps to balance that nucleus. And so in the beginning, when you have just a few protons, it's enough to add as many neutrons to balance things. But as you go heavier and heavier, you have more and more protons, and you have to add more and more neutrons to create a stable system. And that's why as you go heavier and heavier, the whole thing bends over, and you need more and more neutrons to have this kind of stable system. And the last thing I wanted to point out here before moving on to new things is you see some horizontal and vertical lines here. These are what we call the nuclear magic numbers. You can see the actual numbers here. These are nuclei, and I'll show some of their features in a second, but these are nuclei which, if a nucleus has this number of neutrons or this number of protons, it's more stable than its neighbors. So it wants to stay like that. You can describe it in many different ways in terms of energy, but it tends to like to stay like that. So interaction cross sections that tend to be smaller. It doesn't want to capture a neutron. It doesn't want to emit a neutron. It just likes to stay like that. So you will see some of the features that characterize these magic numbers later. And I will also say that these are the magic numbers that we find right on stability. And spoiler alert, this is not true as we go away from stability. So these are the basics to get us started. So as a field, one of the things that this field is working on is to just push everything to the extreme. With physics, research in general, this is the thing that we're trying to do. So for us, in rare isotope research, these extremes can be shown on this chart. So if I choose one extreme to start with, we're trying to go as heavy as possible. What is the heaviest element? So number of protons now. What is the largest number of protons you can have and still have a kind of a bound system, a nucleus that would exist? And so you have to start with, again, something that exists already and merge two nuclei together to create something heavier. And just push it heavier and heavier. We are now at element 118 for oganesson is the heaviest element we got to. But there's predictions that bring us much heavier. There are predictions for something that is called the island of stability, where you see all the magic numbers, that there would be another magic number further up here, and that would create kind of a stable subsystem. My theory colleagues tell me that this was based on kind of simplistic models, and with the more modern models, this is not true anymore. But unless we go there experimentally, we don't really know. It is very hard to get up there because you have to start with, let's say, nuclei that are in this region, merge two together. And again, remember I said, how many neutrons do you have for the number of protons? You're not going to, it's hard to create a system that has even more neutrons than protons that would be over here. If I add two nuclei here, I would probably end up somewhere on this end. And this is what has been going on. So we're always looking for new techniques, new ways of making these super heavy elements. I'll say this is not quite something that EFRIB is focused on, because the energies are too high for this kind of reactions. If you want to merge two nuclei together, you need to have lower energies. So there's other labs around the world. Dubna in Russia, for example, have been leaders. At Berkeley, there have been a lot of discoveries. So you need to have lower energies, so nuclei, when they come together, they will actually merge. The energies that F-rip has, when the two nuclei come together, they will break into pieces. Okay, another extreme is on this end. So it could be, what is the smallest number of neutrons you can have for a given number of protons? So this would be a large Z over N. And you can see here from, well, I should point out that, remember the same colors that I had on the previous slide, they are more or less true here. But now there's also this gray area that shows some prediction of how many nuclei have not been discovered here yet. And so going to the proton-rich side here, you'll see that our colored nuclei already are mostly reaching the limits. This is the end of the nuclear chart. We cannot have any more. As soon as you make more nuclei out here, they will immediately break apart. So it's easier, it's closer to stability, so it's kind of easier to get there to create this nuclei. And we still have, there's some gray colors here, so we still have some missing, but we have gone a long way. The new thing that was discovered as we go to this extreme is that there are new phenomena that start to emerge. Phenomena that 20 years ago, 30 years ago, we had no idea that this could ever be possible. For example, something that's called a halo, proton halo. On the neutron side, we will have a neutron halo. I'll bring it up because I have a nice picture. So a halo is when one or two of the last nucleons in the nucleus, somehow their wave functions are much more extended. So they end up being far away from the core on average than what you would expect. So nuclei, the size of nuclei tends to increase as a function of the number of neutrons and protons they have. But for halo nuclei, there's a huge jump. So a lithium nucleus would have the size of lead, for example. This is how far extended these last neutrons and protons are. And this is something that was discovered about 30 years ago, and no one had predicted it. And we're discovering more and more of these every day. Diproton decay, and it comes together with the dineutron decay on the other side, is again this kind of decay that we didn't know, or you really have to go to an extreme to get to it. And I'll come back into details later. So for now, it's just kind of giving you the big picture. So this is a case where you produce the nucleus, and for some reason, it doesn't want to just emit a single neutron and decay, but it emits two neutrons or two protons together at the same time. And we can see this at the lab and study. This way you can study the interaction between the two neutrons or the two protons, or with the neutron in the core, and so on. We are trying to figure out the location of the dripline. I'll get to the dripline, but this is kind of the end of the stability line here. We've seen structure changes. All these magic numbers that I mentioned before, they tend to change, which is again something that no one expected 30 years ago, and now we see it all the time. New kinds of radioactivity, this proton and neutron radioactivity, neutron skins. So nuclei that have so many neutrons that would create kind of a skin around the central core. So there's a lot of new things going on. So this is one slide that shows you all the extremes in every direction of this chart. And these are not all the only things that are happening within the field, but this is, as a nuclear structure and new discoveries, this is one exciting thing. Okay, so I'm going to do a little bit of go into more details for each of these topics, and that's kind of my goal for today, or at least the first lecture. So to study the structure of nuclei, we need to look at their basic properties. So I have a slide here with a lot of these basic properties. So the mass is one of them. It goes hand in hand with the binding energy. And something I don't have here is the separation energy. So how much energy binds either all of the nucleons together, that's the binding energy, or how much energy binds the last neutron or the last proton to the nucleus. So these are important quantities. As I'll show in the next slide, these are features that help you identify, for example, magic numbers. Another thing is the half-life. So when a nucleus decays, how fast does it decay? How much energy it emits? Which levels in the final nucleus does it populate? So all of that tells about the structure of the nucleus. And again, this kind of new discoveries and new properties of nuclei. We try to look at the shapes of nuclei, and new shapes are still being discovered all the time. I think the most recent that was on the cover of Nature a few years ago was a pear-shaped nucleus. So there's a lot going on with this is kind of what we call a collective behavior of the nucleus. The angular momentum plays a role in everything we do. And then level structure, I'll focus a lot on the level structure because that's the easiest probably thing to understand. But this is, if you're not familiar with the shell model already, this is the same or very similar structure we have for atoms and the electron orbitals of atoms, but this now corresponds to nuclei. So the neutrons and the protons populate these levels separately. So I'll use this a lot because it's just easy to see. Okay, nuclear binding. That's one of the probably the most important properties that we're dealing with from nuclear structure, nuclear astrophysics, in fission, in energy, in everything we do. Nuclear binding, it defines how much energy is going to be released out of your nucleus. If you have a reaction, if you have a decay, whatever you do comes back to the binding energy. So I have the definition here to make sure that we're all on the same page. Binding energy is how many protons do you have times the mass of the proton, plus how many neutrons do you have times the mass of the neutron, and then minus the mass of the nucleus that has that number of protons and that number of neutrons. So there's a difference there. So if I have 10 free protons and 10 free neutrons adding up their mass is different, is more than if I have the protons and the neutrons all bound in the nucleus. And this difference here is what is called the binding energy. A different way to think about it is how much energy do I need to give to that nucleus to just completely break apart into its protons and its neutrons. So this goes into a very nice graph that again gives you everything you need to know about energy production. So the lightest nuclei that we have down here, if you fuse this kind of all these light nuclei together, you end up with kind of the curve goes up all the time. And so you end up producing energy from this kind of fusion reactions. This is the basic principle of how stars produce their energy. It's fusion of these lighter nuclei together. On the other side, again, you see the curve going down here past the iron peak. So on the other side, again, if I would have these nuclei out here, the heaviest nuclei, there's no energy produced if I would fuse two of these nuclei together, it just keeps going down. But if I break it apart, like in the fission, then again, I go back into this region, so I'm again producing energy. So this is the basic chart. For fusion, you produce energy. Through fission, you produce energy, and it all tries to go back into the middle where it's kind of this more bound nuclei. So we will come back to this later when we talk about nuclear astrophysics, but again, this is an important concept to keep in mind. Now, oh yeah.
Can you go back to the previous? So does iron have some special configuration or some special kind of symmetry as to why it peaks at higher for the binding energy?
So the intuitive way that I can think of to explain is through the Coulomb barrier. It's just the nucleus becomes more and more bound. No, bound is not a, well, it does get more bound, but I think it's just adding more and more protons, and then right around the region of iron, it's just the limit. You can also see it in nuclear astrophysics. That's the limit where you can still produce energy. After that, you just have too many protons and they repel each other. So then you cannot fuse anymore. Trying to add another low-lying, another nucleus, another proton, another charged particle into that nucleus, it just repels. So this is kind of the sweet spot, let's say, of how many protons and neutrons you can have to still have a nice bound system. And then once you get heavier and heavier out here, it has too many, it wants to break it apart spontaneously. This is kind of the more intuitive way I could think of, but yeah.
I would like to talk more about how anything larger than iron has to be produced in supernova. If they'll all.
We will, yes, we'll do everything about astrophysics. That's my favorite topic. So you hear more than you ever wanted to know. Okay, So instead of looking at the energy that comes out of if you break the whole nucleus, that's experimentally a little hard to do, to be honest. But measuring the amount of energy for removing one neutron or one proton is experimental is a lot easier, and you can have a reaction and just see what comes out by removing just one neutron or one proton or maybe two. So that's why we define these quantities. They're all more or less the same. Neutron separation energy, how much energy do I need to give to my nucleus to remove that last neutron? And the same for 2 neutron separation energy for removing 2 neutrons, and similar for protons. So this is the first hint that we have in terms of the magic numbers. This is 1 neutron separation energy. The colors here correspond to 3 different elements: tin, antimony, and tellurium. And here's the neutron number. So you see ups and downs. If you haven't seen this before, this is called the odd-even staggering. It's just that paired up neutrons are more bound than if they're individual neutrons, and the same is true for protons. So when they're paired up, they're more bound. When there's a single neutron, it's just easier to remove that last one unpaired neutron. This is how you can think about it. So you see it's all going great and up and down, and it's all pretty flat. And then all of a sudden you get to neutron number 82 and you have this huge drop. This is a feature that would define a magic number. This is just once you're right above, let's say 82 is a pretty stable nucleus, but 83, removing that last neutron is easy. It just wants to get rid of it. If it likes 82, it wants to stay at 82. This is kind of, again, the intuitive way to think about it. A similar feature is here for 2 neutron separation energy for more elements, but it's the same feature. Again, you have this big drop right around neutron number 82. So these are some of the features that we're looking for in terms of identifying structure evolution. How does the structure changes? And is 82 still a good magic number if I go very far away from into very exotic nuclei? Would this still stand or not? In terms of how we can measure it and go all the way to the extremes, I want to take another step by step here and say, okay, in order to measure that neutron separation energy, just looking, I'm giving energy to the nucleus in order to remove that last neutron. And we can have a nice chart like this. It's the beryllium isotopes. It's easy to see. Beryllium-9 is the only stable isotope. And if we look for what is the neutron separation energy, it's 1.6 MeV. So it has this last unpaired neutron. It doesn't take that much energy to remove, but it takes some energy. If I go to beryllium-10, everything is paired up, so it needs more energy. So now we go to 6 MeV to remove that last neutron. And I can keep going like that. Beryllium-11 is only 500 keV. Beryllium-12 is a little bit more, 3 MeV. And then all of a sudden, I get to beryllium-13, where it's negative. So I don't need to give any energy to my last neutron to come out. It will come out naturally. So this is the limit that we call, this is a bound nucleus versus being unbound with respect to neutron emission. So as soon as we make that nucleus, it will naturally emit that last neutron and come back to beryllium-12. Then this is what we call the neutron dripline. This is exactly the limit of nuclear stability, the limit of that chart that we've been talking about. Then you go to the next one, beryllium-14, and again, because of that pairing effect, it's bound again. So once you hit the neutron dripline, it doesn't mean that everything past that line is unbound. It could be bound again, and it could also be the next one. In this case, it's not, but it could. So yeah, beryllium-14 is bound again, and then 15 and 16 are unbound. So this is our definition of what is the limit of bound versus unbound, the limit of stability, or the dripline. You might have heard that. Yes.
More like rotation question, but here, like say in this chart, if you start with beryllium-14, what is labeled 970 is the energy that would take to like take out a neutron and turn it into 13.
Yeah, so it's the energy difference between the ground state of beryllium-14 versus the ground state of beryllium-13. This kind of energy difference plays a role in everything we do. This is what defines if a nucleus will beta minus decay or beta plus or alpha emission or fission or whatever. It's the energies or the mass divided by the mass of the first nucleus and the last.
Right, so if you say start with 13, then measurably it will turn into 12.
So 13 would immediately decay to 12, yes. 14, as it looks here, it would decay to 13 and then to 12. If you could, okay, 14 is bound. We'll go into details, but it's bound at its ground state. But if you had a little more energy and you excite it, then it would be unbound and it could decay.
Okay.
Another thing that I don't know if anyone has good eyes and noticed here, beryllium-16, I have it as white and I say it's beyond the drip line, but its binding energy is positive. So it should have been bound. And it is bound with respect to 1 neutron emission, but it's unbound with respect to 2 neutron emission. So it doesn't, energetically, it does not emit a single neutron, but it can emit 2 neutrons together. And I'll come back to that later. This is the dineutron decay that we talked about. Okay, it's already getting pretty fast there, but this is, I prefer to go slow and explain things, but here's the whole neutron drip line. This is how we can mark it. And these nuclei do exist. It's not that they don't exist. They just exist for such a short time, like 10 to the minus 21 seconds is the limit that we're giving. And but still, they are nuclei. We can study their ground state. We can study the excited states. We can study their structure. It's just that they're emitting neutrons instead of doing anything else. Okay, I think I'll skip this. I want to do one last thing here before we have a break. And this is in terms of the nuclear structure that I talked about. So when the other thing we study in terms of the evolution of nuclei is using the structure of excited states within the same nucleus. And this would follow the shell model as well. I'm not going to go into the differences of going for the splitting of the spin orbit and whatnot, but this last part here is what happens in reality. And you see the big gaps right at the magic numbers. So magic number 2, magic number 8 is again a big gap. Magic number 20 is a big gap. So remember, we saw it as a function of how much energy do I need to give the nucleus to remove that last neutron or the last 2 neutrons. Here you can also see that if I have my neutrons, let's say 20 neutrons sitting all the way up to this level here, it would take a lot of energy to excite that neutron and bring it across the n equals 20 gap. But if I only had, let's say, I don't know, 10 neutrons, and my 10 neutrons were sitting all the way up here, it's just a small distance, so I only need to give a little energy to excite it. So the energy of the first excited state in nuclei is again another indication of this structure evolution. So this is what I wanted to play with here with my neutrons and my protons, just to give you again a little taste of what that looks like. So these are 2 nuclei, neon-26 and oxygen-14. These are the level structures from the shell model, and this is how the protons would be placed, and this is how the neutrons would be placed. I like this. This is what we call a single particle structure, and I like this because it's intuitive. It's easy to see. Okay, I get 1 neutron and I excite it up, and this is what happens. When you go to heavier nuclei, things get a lot more complicated. You have collective effects, you have vibrations, you have rotations, and this just makes things a lot easier. But I like these kind of explanations. It's much simpler. So let's say I want to look for the structure of neon-26, and I want to see where the first excited state of neon-26 is in order to see is it a magic number or not. We're talking here about n equals 16. It shouldn't be a magic number at all. It should be just a small gap here. So we're trying to see what's going on. So the idea is that somehow you give energy to the nucleus to excite one of its neutrons up. This can be through a reaction. It can be you're starting with another nucleus and you're adding a neutron, you're removing a neutron, you're removing a proton. There's many different ways to do this, but somehow you end up with a configuration where you have this neutron excited to the next level. It will almost immediately de-excite down and emit a gamma ray, and that's easy. It's an experimental rays. I have my detectors. I measure those gamma rays. The same thing can happen with oxygen-24, and you should already suspect, okay, what's going on? Oxygen-24 still has 16 neutrons, but I am drawing the gap there to be much larger. but it's the same story. It de-excites and emits a gamma ray. And now if the gap is larger, I should have the energy of that gamma ray should be larger. It's exactly the difference between the levels. And this is exactly what is happening. So this is that 2 plus is the first excited state. If I'm looking at the first excited state in a whole bunch of different nuclei, carbon, oxygen, neon, magnesium, then black here is oxygen. And as you can see, when we go to neutron number 16, that gap, that first excited state is much larger than anything else. So this is again an indication that what we were calling magic numbers before, so magic number 8, it has a huge gap. So this was a classic magic number. Now we go to more exotic nuclei, and this is again creating a big gap. And it's not true for the other isotopes. So neon 26, which would be this guy here, is not a big gap. But oxygen it is. So this would be a new magic number, and we need to figure out again new discoveries. And we need to work with theory to understand what is causing this kind of evolution, go back, have new predictions for which other nuclei should see this feature, measure again, and we kind of go back and forth and trying to understand this kind of evolution. Yeah, maybe it's useful to show here. So oxygen, what is that? Oxygen 24. Here are my oxygen isotopes. So oxygen 24 is out here. So it's quite far from the last stable oxygen, which is oxygen 18. That's what I want to show here. So it's, as we go far away from stability, this kind of new features pop up. I think I will skip this. This is all the population, different ways to populate that I was talking about. Maybe 2 more minutes to introduce one more topic and then we'll stop. So we talked about the nuclei beyond the drip line. They will not emit gamma rays and stuff. They would emit a neutron because they're neutron unbound, but we can't measure that neutron. And the same is true for the proton drip line. We can measure those protons that are coming out. The protons tend to slow down again because of the Coulomb barrier. They come out more slowly, and because they're charged, they interact with our detectors a lot easier, so we can really see what's going on. And I had the picture before. I think I have the picture again. I'll go a little back and forth. There you go. So for the protons, we can see the 2 protons inside our detectors very clearly. And you can see that they're coming together, what angles they're going to. You can measure their energy. It's beautiful. With neutrons, it's a lot harder because neutrons don't interact so much with our detectors. But still, we can measure these quantities, just not in such an obvious way. So one of the things we've been doing is, now going back. So one example is shown here. There was a whole story, it's about a decade now old. There was a whole story that talked about oxygen 26, is it bound or is it unbound? So again, discovering the limits of stability, will it exist, will it not exist? And then we talked to our theory colleagues and trying to get a prediction. Sorry for the theorists in the room, but the prediction were not. So these are a whole bunch of different predictions, theoretical predictions, and they predicted the oxygen 26 to be bound by 5 MeV or unbound by 5 MeV, and they were just all over the place. So this was a big thing again a few years ago, and every group in this subfield was trying to do measurements. There was one in Japan. We were trying to do it, and in Germany they were trying to do it. We beat them to it, and we did the first measurement. And so this gray line here in the middle was what we actually measured. So we found that it was unbound by just a tiny little bit, just 100 kV or so. So this is again one of the games that one can play is trying to figure out the location of the drip line and try to figure out, again, discovery, is it bound? Will I see it in my detector? Should I just see the products of that decay in my detector? And then once it is unbound, then you can look at the products, like in this case, it's 2 neutrons. And we saw for the first time that the 2 neutrons were coming out together as a pair. So that was the dineutron decay. So I think instead of rushing through, I'll stop here. Gives you a flavor of the different exotic phenomena that are going on in rare isotope science. And based on your questions, I'm happy to dive more into details. So why don't we take like a 7-minute break so you guys can discuss with your neighbors, and then we can do a question session.
Yeah, I think that for the students online, I'm gonna create 3 breakout rooms and to let you chat within each other. And so let me try to do it.